I/O device, are you done? Are you done? Are you done? And because that looks to the CPU like we can do real work, at the end of my time slice, I'm just going to go back to the runnable list. And at some point, I'm going to be scheduled again. If the event hasn't completed, then I'm going to ask, are you done? Are you done? Are you done? Over and over again. Okay? The block state, in a sense, moves the process out of the way while it cannot get any useful work done. Okay? The CPU itself can't tell that. What we wind up having to do is the operating system is going to look at this. Okay? When we do any kind of a system call, that can result in a yield, right? A context switch. And what type of context switch would that be? Voluntary or involuntary? Let's go ahead and vote. Voluntary? Context switch, you can make a system call. Involuntary. What do you say voluntary?
Because it's requested the system calls is expected a context.
Yeah, so the system calls are invoked by your code. We can look at your code, see the system call, and you're deliberately making the system call. The system is saying, if you make a system call, we reserve the right to do a context switch. Okay? So that's voluntary. You didn't have to use the system call. You voluntarily made those calls. The time slice expiring, the timer interrupt going off, though, is completely involuntary, isn't it? Completely involuntary. It has no control. And we've talked about the concept of the virtual CPU. Now, remember we gave the process its own CPU, virtual CPU, but it couldn't do protected operations. Okay? So now what we have when we're doing context switches, we're really taking someone's virtual CPU out of the real CPU and loading someone else's virtual CPU back in. Okay, and that's the CPU state. Okay. So, we saw that when we had unused time on the CPU, if we could take some other job and let it use the CPU, we got something very, very valuable, which was called schedule compression. Okay, and what did I mean by schedule compression?
The actual time taken to compute is smaller because when something is actually waiting for like a disk or I/O, other processes can actually put in the CPU and actually use that time.
Yeah, so what we're going to do is we're going to notice when the CPU is not when the CPU is not busy, and we're going to say let some other process use it. Okay. So now up here we see A wants to use 90 units of time to get done, but it's not using all of that time productively on the CPU. So if we turn around and places where it's not doing productive work on the CPU, we let process B run in there, and process B is going to be 30 units long, right? It turns out, sorry, 50 units long. Turns out we can press the schedule. We go from a schedule of 140 units down to a schedule of 100 units. What will be happening in that first table? What's happening with these? This is what we talked about before, that if we don't have a mechanism for dealing with I/O and I/O gaps, all the process can do is say, are you done? Are you done? Are you done? So it's still using the CPU in that gap. It's just not doing productive work because it doesn't have any other way of determining when the I/O is complete. Okay? But once we start using I/O interrupts and the sleep state or block state, we're able to say, hey, if you're doing I/O or some other system call that's going to take a while, we're going to put you here into the block state. So now you can't use the CPU. We'll let someone else use the CPU, and they'll get it in time sliced chunks. Okay, and then when the I/O is complete, there will be an I/O interrupt posted. We'll get that after one assembly instruction. And we'll be able to go into the sleep state on our diagram and take that process or processes, because it could be more than one, that are waiting for that event, and move them to the runnable state. Because now, when they ask the question, are you done? The answer is yes. Does that make sense? We're going to do that.
Like, how many steps or how long does it take to perform a context switch? Because it obviously has to happen all the time. So we kind of slow things down.
Well, how many steps are there in a context switch? Okay, and inside there, there's two context switches. Right? There's the first context switch that goes from process A to the scheduler, and then the one that goes from the scheduler to process B. Take a look at our code in switch.c. You'll see that it's 20 assembly instructions, okay, for the context switch. And if the time slice is, say, 10 milliseconds, and our CPU can execute 3 instructions per nanosecond, we can get a lot of instructions done.
Okay, so it's missing the order of magnitude. So yeah, so it's like
So yeah, it seems like a small amount of time, this time slice, but compared to the amount of time it takes to execute an assembly instruction, it's relatively large, millions of instructions, right? So the context switch, though, we need the overhead to be low. And we've been studying as we go along here, we've been taking a look at the middle part. Remember that middle part of that 5-step diagram is running the scheduler algorithm. Those are what we're currently studying. And as we've been going along, okay, we started off with a very constrained environment, and we looked at what was optimal there, and it turned out had very, very low overhead. But once we started to let our environment become more flexible, it turned out that these algorithms had very low overhead, did not do as good a job as we would have liked. Okay. It sort of became an issue. But we were able to find different ways to do, let's just say, good enough. All right. And we ended last time, we had added in I/O, and when we found that, being able to take those empty times on the CPU by putting that process A into the block state and give it to process B, we're getting the illusion of a faster processor because we completed more work per unit time. But it's not a faster processor. We're just using it more efficiently. Okay. If you think about that schedule, we went from 140 units down to 100 units. Okay. That's a pretty big cut. And we did not do it by putting in a faster processor. We just added a state to our state diagram and had I/O interrupts so that we could rendezvous later, and that allowed us to take these gaps in the CPU and give them over to another process. So now we have a context switch. Each one of those changing colors is now a context switch. Okay. Over here, we're using context switches. We were letting them run for a big amount of time. Or if that was within a single time slice, and this is where the huge benefit is, I just enter into my time slice, and the first thing I do is, well, pretty quickly, is I/O, because I'm an interactive process. Okay. Now, rather than sitting around for the rest of my time slice, if they give that up to somebody else, then we're going to continue to compress the schedule. Okay. So in interactive jobs, this diagram on the left, for A, that's how those processes look. Computation I/O, back and forth. Okay. But most of the time it's going to be spent doing I/O, whether it's a disk, keyboard, whatever. Okay. So now we're giving that illusion of a faster CPU by being able to take advantage of the dead time, that is the time on the CPU where we're not doing productive work, and give that to another process. Okay. Now, let's deal with starvation. Okay. We kind of remember when we went from the optimal algorithm, shortest job first. Well, it was couldn't be beaten, and then we allowed a late job, and now we can't use it. Okay. Let's think about how we can address starvation. And the simplest one, the one that our XV6 OS currently uses, is called round robin. And round robin is based on a FIFO. Okay? So it looks a lot like the FIFO scheduling that we had before, except now we have time slices. So things change in terms of our opportunities. Okay? So round robin is pretty good for interactive jobs. We'll see where we can do better. But it also doesn't hurt long-running jobs. Okay. So now we're going to redefine what a job is. Remember before we had a process that came in and ran forever. We knew how much time it was going to take. We could run it in chunks. Now what we're going to do is say that when a process arrives at the back of our FIFO queue, it's a new job, no matter how it got there. Okay? That means if my process is currently in the CPU, and my time slice expires, and I'm taken and put at the back of the queue, I'm now considered a new job. It's the same process, but as far as the schedule is concerned, it's a new job. This gives us something beneficial. Did we do the whole response time trick of giving us good response time but having really lousy response time? Did we do that one last time? Let's do this. So the response time says you have good response time if the time between when you first get into the CPU and the time that you arrive at the back of the queue is short. Okay? But it was first run, wasn't it? Okay? So let's say you're a job that just arrived at the back of the queue. Right? And we quickly get you through and give you the CPU. Right? And then your time slice expires, so we take it back and we never give it to you again. Have we starved him?
Technically, yes, because you're never going to get the...
I'm never going to give it to him again. But by the definition, did he have good response time?
Mm-hmm.
Okay. All right. Does this not hurt your brain? How can an interactive job that never gets the CPU have good response time? Well, we'll give it to him once. That's all we needed to do. Okay. So that original definition of response time was not really mapping the world very well. So instead what we're going to do is every time you go to the back of the queue, every time you show back up in the queue, you're a new job. Now when we talk about response time, it's the amount of time it takes for your job to get through the queue. And this means that interactive jobs are not just measured once, they're measured every time they're in the queue.
Can you give some examples of interactive jobs?
Oh, interactive jobs, sitting at the keyboard, what you're doing right now. Okay? Your computer's doing some computing, then waiting for you to type, right? So that's you're interacting with, the computer's interacting with the environment. Or maybe it's a payroll program. It reads some data in from the database, does a bunch of calculations, figures out who gets all the many 600 pieces of your check that total 104%. And then how much money you get, and then it writes your check. And then it goes off and it does the calculations again for the next one. Okay? So it'll be a period of calculation, period of some kind of I/O interacting with the environment, followed by some period of calculation. Okay? The example I really like is how many of you have ever been like reading email or something like that, and then went to dinner or went to sleep? but your poor little email program was just sitting there going, please, please, read my email. Okay? All right. That's interactive, but it's really quite slow. And the interesting thing is we don't want that program eating up the CPU going, please read my email. We don't want it doing that. Okay, so we give it up and give it to another process. So the jobs now is, as we can think of this as one job that we were thinking about before, job A. We're now going to break it up into lots of little chunks. Okay. Now, it says here that there are time slices in length, and I meant to fix that this morning. They're at most a time slice in length. Why at most?
If it completes whatever it's doing before the time slices.
Well, yeah, if it calls exit and it's done, yep, that could be less than time slice boundary. What else?
Any voluntary context switch.
Any voluntary context switch. Okay. So it doesn't, we don't say, I will give up the CPU as long as my time slice is expired. The voluntary context switch is, I'm going to do I/O or something else where it makes sense for me to give up the CPU. So I'm going to voluntarily give back the rest of my time slice. Okay. They're interesting to know that time slices are independent of processes. So if you give up your time slice early, and someone else, some other process goes into the CPU, it only gets the remainder of that time slice before the scheduler runs. Okay. And the reason being is that the overhead to actually reprogram the timer interrupts is just ridiculous. Okay, so instead, we've been counting timer interrupts, and we say, oh, maybe after every 10 timer interrupts, we'll call the scheduler. To go back in and reprogram that on the fly, every time we have a voluntary context switch, is, let's just say, inefficient. And we'll leave it there. So, the nice thing about a FIFO is it's a totally ordered queue. Okay. And you guys have studied, and was it 251 where you talk about partial and total orders? And ideas. The idea of the FIFO is we have a total order. Okay, and because it's a FIFO, we have something interesting that we could say about starvation. And that is, we can't have any. Does anybody know why? We cannot have starvation.
You always go in the back and come up front, so there's no way that you can like get kicked out. There's no way you can skip a process. Yeah. There's
No way you can skip a process. Yeah, I mean, we'll combine these two, and basically what we wind up with is that your maximum delay, maximum possible delay, are the number of processes ahead of you in the queue times the size of a time slice. It's bounded. Okay? And everyone goes in the front, and the next ones are taken off the front. There's no way to change the order. We do not sort. Okay? And this is ridiculously powerful. Right? Just really quite cool. We go, hey, is there anything on the queue ready to run? Okay, is there anything on the runnable list? If the answer is no, we go, oh, well, we'll come back. If the answer is yes, we take them and we run them. And then when it's time for them to come out of the CPU through a voluntary or involuntary context switch, we put them at the back. Any new job that's created, new process gets created in fork or something like that. It puts the job in the back. Okay? So we have a bound.
So say you had an unlucky process that kept being put behind something that was a short process, but it itself took a longer amount of time. So if it kept being switched into just a piece of a time slice, then eventually would that starve?
So this is I'm going to make this observation for about 5 minutes, but if we're only getting pieces of time slices, and that's all we ever get, we're technically not starved. We're not getting an entire time slice, are we? Okay. Now, because the execution of processes is asynchronous to to the time slice, we can say that the penalty for those that get small amounts of the time slice appears random to the job stream. And therefore, we're equally unfair to everyone.
Okay.
Okay? You notice how I didn't say we're fair. I did not say we're fair. We were unfair in a fair way. And that's important. That's actually a kind of a deep insight into there. When you go, well, what if I'm that unlucky soul? They go, it's random. It should affect everybody. But yeah, there's a degenerate case where you always get 1 nanosecond. Boo-hoo, sucks to be you. Okay, I mean, there's nothing we can do about it. The only other way to do about it would take so much time and overhead that we take 90% of the time slice to do our scheduling. And then you'd still get just that 10%. But what we want to do is we want to have the smallest amount of overhead. And with that, we're willing to deal with certain statistical issues. And in this particular one, you might, for a period of time, have an unfair shot. I mean, not unfair shot, but you might get less of the CPU than others are getting in your time slice. But overall, it should average out to be, as I said, equally unfair. I'm not going to say it's fair at all. I'm just going to say that it's equally unfair.
I see, because it's sort of considered to be random.
Everybody's get this equal chance of getting that exact same penalty. But I can guarantee I don't have starvation, because even if you only get in there for a nanosecond, you still got a nanosecond. Okay?
Okay.
All right. See how and we can sit here and quite easily, as you spotted, what operating system of its right mind would do that to its processes? Well, we're studying the basic algorithms. Okay. So all we're trying to do is get a feel on them. And one of the ones we're going to get a feel on is that, hey, there's still unfairness in here. And then of course we're going to go, but it's fairly unfair.
Okay.
Okay. So statistically, everybody gets the same chance at unfairness.